Okay, now we're going to talk about triple integrals in cylindrical and spherical coordinates. So, I have a bit of a blurb mentioning um, the fact that the reason that we might switch over to cylindrical and spherical coordinates for computing our integrals is typically because the domain that we integrate over is more easily expressed in that manner. That's usually what will tip you off that you're going to want to convert over to a different coordinate system. Um, Although there are some instances where the coordinate system you want to use can be based around the function rather than the domain itself. So there's a bit of interplay between these things, and you might need to try one thing or try the other thing. Um, with a bit of practice, you will perhaps be able to tell more readily which coordinate system ought to work. But yeah, so both the domain that you integrate over as well as the integrand, the function you're integrating, um, play a role. They factor into your consideration for which coordinate system you want to integrate with respect to. And also, when you do the conversion process, you have to remember the Jacobian. So that's the additional factor that you put into your integral in order to um, deal with the fact that in these other coordinate systems, the grid is warped. So I'll mention this later down in the notes, but I'll mention it right here. So for cylindrical, the Jacobian is simply R. So attached to this, it's like R times dr d theta dz. And then for spherical, the Jacobian is rho squared sine phi. You don't have to memorize this. These things are going to be a part of the formula sheet. They're part of the differential element of volume. But when you work with this stuff enough, and especially because like you want to make sure you don't forget it, it can be convenient to just like remember the fact that the Jacobian for cylindrical is R, the Jacobian for spherical is rho squared sine phi. So whenever you're converting an integral from Cartesian coordinates to cylindrical or spherical coordinates, you have to tack these you have to tack one of these multiplicative factors on as part of the end of your integral. I usually write it at the end because I want to make sure that when I look back on my work, that I can easily see that I did not forget those things. It's like a very simple mistake to make to forget this Jacobian, this factor. Okay. Um. So first, I'm gonna talk about the material, so cylindrical and spherical, before getting onto the example problems. I'm doing this because it kind of makes more sense to do it in this way. Like when you're presented with a problem, you aren't going to know which coordinate system to use. So, although in the homework it is kind of structured, you can kind of tell like the first two are cylindrical, the last two are spherical, but in practice, say on the exam, you're not going to know off the bat which coordinate system to use. So that is a question you have to be thinking about. Like, given this problem, given this domain, given this function, which coordinate system makes sense? So I'm going to just sort of treat it in that manner. All right. First, by just giving you the information, and then by looking at the problems. Uh, and yeah, at the very last part of these notes, I have some hints for the exercises, which the hints are just actually the final answer you should get. So that you can check your work, I suppose. Okay. So to start with, you should recall that we had conversion formulas for cylindrical, and I'm just sort of bringing them back up just to reload them into memory in case you forgot. So x is r cosine theta, y is r sine theta, and the z stays as z, right? Because cylindrical is just polar plus the z-axis. And well, the radius squared is equal to x squared plus y squared. That makes sense from the triangle, right? The triangle that combines polar with Cartesian. So you got this kind of I'm drawing it too small. You have right triangle, theta, radius is r. This would be whatever the x value is, whatever the y value is. And so you have this kind of, from this triangle, you can read off these conversion formulas. And yeah, there's a way to get to the angle from the ratio of sides by doing, oh wait, I did that, I labeled it wrong. Y here and X there. Y over X, take the arctan of that, and that's how you get theta. Okay, so instances where you might find cylindrical coordinates coming into play, well, it can be when you have regions that are related to these kinds of shapes. So, for instance, if you have a circular cylinder, in this table I grabbed from the book basically, but so a circular cylinder, right, you can, that's just something with a circular base and some kind of a height that extends. That is easily described as being r equal to some constant. That constant is the radius of the cylinder. So if you're integrating over the three-dimensional region that is defined by the cylinder, then you would have r ranging from 0 to c, and then like theta going from 0 to 2 pi, and then z being whatever the height is for the cylinder. For a circular cone, you have that z is equal to cr. I guess you could start off with this formula, and then you could notice that this quantity is r squared, and then you would take the square root of both sides, I suppose, and that would reduce you to this. So I'm going to represent this with the following type of picture. So r here is the sort of the radial axis. You can think of this as the x-axis and y-axis kind of squashed, so the plane, the xy plane, squashed into a single axis, and that this is z. So the fact that you have this is a linear relationship between r and z. That means you have some kind of a slope. That slope ends up defining the cone. So you can imagine that, well, when we turn this picture, maybe I should use a different color for this line itself. When you return this picture to three-dimensional picture, what you're doing is maybe I should also make it so that r is always thought positively. What you do is you're basically revolving this around the z-axis. So then r ends up becoming the xy plane, and then this this line in green ends up tracing out the cone. Okay, so that's one way that I think about these pictures. Okay, with the sphere you can see that, well, x squared plus y squared can be combined to be r squared. So you have this way of writing a sphere. This can sometimes come into play, but when you see a sphere, often, at least my impulse would be to try using spherical coordinates rather than cylindrical. But there are certain problems where it makes sense to use cylindrical, even though you're presented with some kind of spherical equation. So you have to be a bit careful about this kind of thing. You can see that that's how you convert it. And then for a paraboloid, well, c is how much you stretch the parabola. You can see that this ends up being r squared, you have z. So you end up with, well, it's a similar picture. If you have r here and z here, the relationship you end up getting is a paraboloid, a parabolic kind of shape. And then, of course, you rotate that line segment about the z-axis, and that traces out a paraboloid. Okay. Right, so now we have this Fubini's theorem. So, which effectively says that when you're given this triple integral over some region that's not where the integration order isn't specified, well, if the region is a cylindrical box, which is of this kind of format, where you have that r is bounded by constants, theta is bounded by constants, and z is bounded by constants, then you can rewrite this integral into cylindrical. So notice that there's not just the bounds that are changing, but also the function is changing, which is being described here. So g was described in terms of x, y, and z. But then to convert it over to cylindrical, you replace out x and y with the polar counterparts, or the Cartesian counterparts, which are r cosine theta, r sine theta. And then when you actually do that, you end up with an expression that involves r, theta, and z that you would then collectively think of as the function f, right? And then notice that you have this r showing up. So that is the Jacobian in um, cylindrical, which is also the Jacobian in polar, right? Since in polar we had r and theta, which accounted for the area distortion. The z doesn't have any area distortion. So the Jacobian ends up being the same for cylindrical and for polar. And like as a final check, let's see that the bounds for the integrals match up. So r goes from a to b, which is exactly specified here. Theta goes between alpha and beta, which is there. And then z is bounded between c and d, which is there. So this kind of not fully prescribed, well, I mean, it's prescribed in some sense, but it's like abstractly defined. It doesn't tell you how exactly to perform the integral. It just says integrate over the region B, right? This integral can be represented, according to Fubini's theorem, as this iterated integral, okay? And then what's convenient to do is if this function can be split into a product of functions that just involve r, theta, and z, then this entire triple integral can be split into a product of three one-dimensional integrals. So that is like the nicest situation that can happen. And it does require that you're integrating over a cylindrical box where all of these bounds are numbers, right? If you have any kind of codependency between these things, like if r depended on theta, or theta depended on z, or r depended on z, or some other kind of dependency, then you can't fully split things apart. You have to, some parts of it maybe you can still split, but you'll still have to treat part of it as being an iterated integral. I don't think there's an example of that in the homework or in my examples, but such examples can show up, so just be aware of that. Okay. Now we're moving on to spherical coordinates. So again, we have these kinds of conversion formulas, and perhaps I should just briefly refresh how the angles work. So remember that theta is the same theta as in polar, right? So if we write out the x and y coordinate system in this way, so in order to get to this, you have to tilt this a little bit to get the axes like this. So then theta is measured in this kind of direction, right? This counterclockwise orientation, right? Theta is equal to 0 at the x-axis. It will be pi over 2 at the y-axis, negative, or it'll be pi at the negative x-axis, 3 pi over 2, and if you go all the way around, well, that you could call that 2 pi. Okay. All right. And I guess I can also mention there are some instances where you might want to name these things a bit differently. I do have an example of that in below. The point to make about this is you don't want to switch the order that you move across. You don't want to flip the theta direction. So you want theta to remain counterclockwise. So I'll probably re-mention this, but I have an integral that's like this, from minus pi over 2 to pi over 2, and I also, I believe, have an integral that is like this, from pi to 2 pi, or I think I named it from minus pi to 0. So the main thing is you want to keep the counterclockwise orientation, otherwise you end up introducing a negative into your calculation. Just as how with like one-dimensional integrals, when you integrate from you integrate from left to right, and you know that if you all of a sudden have the integration going in the other direction, that's as though you've introduced a negative, right? That's like the same as if you integrate from 6 to 2, you know that that's equal to negative integral 2 to 6. This kind of thing is the issue that can arise if you end up switching the orientation that you integrate in. So one thing to mention is keep the correct integration order. Like this kind of integral, you could have thought of it as 0 to pi, but that would actually be in the wrong quadrants. If you did 0 to minus pi, then you will have integrated in the opposite direction. And so those are issues that might introduce negatives, and they're problematic. So to avoid making a mistake, you want to keep the correct orientation with respect to theta. Okay, so that was theta. Okay, so rho is pretty obvious. Rho is the radius, or yeah, it's how far the point is in spherical. So it's x squared plus y squared plus z squared, all in a square root. The other angle is phi, right? Which I called the angle of inclination from positive z. So what you do is you start at positive z, and this has the angle phi is equal to 0. Then you angle yourself downward, and then the furthest negative you can go is in the direction of negative z, which has the angle phi equals pi, right? One way that I can depict this is if I think of it in terms of this r and r and z. If I flatten the xy plane down into a single line, then we have this kind of picture. I don't like that this is kind of skewed. So we have this kind of picture. So you can see that over here, in this angle, we have phi equals 0. In this part, we end up having phi is equal to pi over 2. And then down here, we end up having phi. So phi is equal to pi there. Yeah, my handwriting's a little bit. Phi is equal to 0 there. Yeah. So hopefully that's more clear. The fact that phi is angle of inclination from positive z. So it's the angle that you use to get to positive z, and the orientation again is something that may factor in. So you should always be. Phi is actually oriented clockwise, as you can see from this kind of picture, and I would always draw this kind of inclination going in this on the right side, because the right side is where you have like the positive radial direction. Okay, I think that's enough about those angles. So we have these conversion formulas. I think they should look quite familiar to you, although we only used them briefly a few chapters ago. But you can look at them again and refresh yourself on how they work. So notice that this denominator is actually rho. I know that Katie likes to write this as z over rho. And I don't know what else to mention about this. If you square x squared, if you do x squared plus y squared, you can actually simplify that quantity a little bit, because you get a cosine squared theta and a sine squared theta. So that quantity ends up being rho squared sine squared phi. I think that shows up in one of the example problems, but not that important. Anyway, so now some regions that are convenient to do in spherical. Well, certainly the sphere itself is easy to talk about. Right? That is simply just let rho equal to some constant. If you're talking about a plane that passes through the origin, and I guess specifically it has to contain the entire z-axis, in fact, right? So in that case, then that's described by just theta being some angle, which I think is pretty apparent from thinking about this visually. And now we have this important example, which is cones. So cones, I think cones are worth all the trouble some things lie. Some of these problems involving cylindrical and spherical can be quite tricky. And when you start encountering cones, it is maybe when things get a bit more problematic. So certainly a cone can be described as being phi, the angle of inclination being some particular constant, and then you can sweep out over phi. The problem is you can also define this using cylindrical. So because in terms of cylindrical, it's described as a linear relationship. Z is equal to c times r, which I think is a relationship that was written above, right? So once you encounter cones, the problem can be done sometimes can be done in either coordinate system, and you have to wonder which one is more convenient. That may depend on the region. That may depend on the function itself. I know from experience that um, a big factor that typically helps to figure it out is whether the cone has a spherical top or a flat top. So, in practice, like I remember seeing that for cones with a flat top, you usually want to use cylindrical, and cones with a spherical top, you usually want to use spherical. But I wouldn't take that as a rule. I would use that as kind of like a guiding principle, and still have to, just double check myself to make sure that everything is working out in the right way. And again, these kinds of problems can get a bit tricky. All right. Right. So integrating in spherical. So I think this wasn't mentioned before, but a spherical box, you can probably guess what it is, right? You have that all of the variables are bounded by some constant values. So rho, the radius, is bounded between values a and b, some constants a and b. Theta is bounded between some constants alpha and beta, and phi, the angle phi, is bounded between some constants gamma and psi. Um, it's it's a understandable convention that like the angles are written in Greek letters, but if you're not careful, it's easy to confuse phi and psi. So just be careful about that, I suppose. Um, this illustration here is to kind of show you where the differential element of volume, how we end up arriving at it. Although I find that I haven't fully thought through this picture, but I'm fairly sure that this arrow is not pointed at the right thing. This should be a side length, but it should be in particular. I'm fairly sure it should be this side length, but I haven't completely thought through it. But it ought to be one of the side lengths because you end up multiplying all three of these sides of this cuboid together in order to get the differential element of volume. This thing that is like the infinitesimal volume element. And notice that we have this rho squared sine phi. That is, as I said, the Jacobian for spherical, right? So you can see that showing up in this Fabini's theorem for spherical. So if you have a function that is continuous on a spherical box, like so, right? So rho is between a and b, theta is between alpha and beta, and psi, no, not psi, phi is between gamma and psi, right? This kind of box. Then, yeah, I don't quite like how it's already. Okay, so it didn't try to define this like converting over from Cartesian to spherical, but you can kind of imagine the analogous version to what was up here. That if you had the function in Cartesian, you'd have to insert in all the variables to convert it over to a function in spherical, and then the Jacobian would show up. Here, because this integral is already written in terms of spherical coordinates, there's the Jacobian already there. And so it's not quite as bad as saying triple integral of the function over some volume with respect to some volume element. So you could have written it like this if you're trying to abbreviate things and not even mention what coordinate system the function is supposed to work in. But once you notice that B is supposed to be a spherical box, then that kind of tips you off that you should be using spherical coordinates. You would convert over the function f to spherical, you would introduce the Jacobian, and then your dv would expand out to this entire thing. Maybe I can mention that this whole thing is what you would call dv. So the differential element of volume accounts for it takes into account the Jacobian, the warping of the coordinate system. And again, the way that these integrals link up should should make sense to you. So the innermost integral is the integral with respect to rho, and its bounds are from a to b. The next inner one is this middle guy. This integral is with respect to phi, and it's bounded by gamma and psi. And then you have the outermost integral being theta from alpha to beta. And well, again, this is an iterated integral, right? The way that you would do this, if there weren't anything fancy about any simplifications that you could do, the way you'd have to compute this, if you didn't have any simplifications, is you'd do it inside out. You'd compute the inner integral, then the next inner integral, then the final outer integral. You'd work inside out. But if you have convenient things, and we have half of the convenient stuff going on already because all of our bounds are constants, if you have in addition that this function inside is easily expressed as a product of functions that are just functions of, well, a function of rho times a function of theta times a function of phi, then you could split this triple integral into a product of three one-dimensional integrals. And that's kind of the most convenient thing that you could do. Okay. And oh yes, so this order is not 100% necessary. You can do any of the 6 integration orders. You can permute these Greek letters any of the 6 ways that you want, because this is a box, right? So because this is a box, switching the order of integration is fairly straightforward. You don't have the kind of like the dependency. You don't have like one of the bounds depending on like you don't have the rho depending on phi. So because you don't have dependency there, you don't have to think about how you would change the function that describes the bound in order to be able to switch the order of the integrals. With boxes, you can just switch them without really thinking. Okay. So yes, any of the other orders is doable. All right. So now for some examples. So for this first example, we're told to evaluate this triple integral, and we're given this function. So I'll just mention that I changed a few things compared to your problem. I'm fairly sure, if I remember correctly, I changed your function. I think I changed this radius, and I believe I changed this quadrant. Okay, so so the first thing is trying to determine whether you should be using spherical or cylindrical, I would say, right? A priori, we don't know which coordinate system to use. And so for that, I would stare at well, not just stare at this, I would try to visualize what this region B looks like. And so, well, notice that Z is bounded between 0 and 1. So that is actually a strong tell for me that this is cylindrical. The other thing is, now we can look at this, and this should scream at you that this is saying r squared is less than or equal to 16, which is saying that r is between 0 and 4. Okay. So when I see this, that's what I immediately try to do. And then noticing these two, this requires me to draw a bit of a sketch. So I just need to think about what quadrant this is isolating, because these two are actually they're cutting the xy plane into, like, they're halving the xy plane. So the first condition is saying that x must be less than 0, which is telling me it has to be in these two quadrants. And then the other condition is saying that y needs to be greater than or equal to 0. That's telling me it needs to be in, well, I guess technically these two quadrants. So altogether, that's saying I have to be in this quadrant, in quadrant 2. Okay. And so, this allows me to convert everything over. So what I'm going to do is I'm also going to express this this condition. So this condition is saying that theta goes between pi over 2 and pi. I tend to write it in this way, but for the first two examples, I actually wrote it with inequalities because that seems to be what the textbook's convention. But you'll find that I will resort to this in like the last two example problems. Okay. But this just means this condition, right? Theta is between pi over 2 and pi is the same as this triple inequality here. So you can express this in different ways. And so I think you can see that I was able to convert all of these conditions into conditions that are in cylindrical coordinates, which has allowed me to convert the entire region B into, well, to be able to describe a B in cylindrical. And not only that, we can see that this is actually a cylindrical box. Okay, so that's kind of nice. So now that we know that, I would then convert over the function. So I've kind of written these out of order. Now that I know that I want to use cylindrical for this problem, I would convert over this function. So x, if you recall the conversion formulas, x is r cosine theta. So that's why this r cosine theta shows up, and then times z. Right. So what we are trying to do is to evaluate this integral over this region. Oh, that's funny. I switched between letters. I don't know what happened there. That's funny. So, oh, okay, that's the book did the same, or at least the PDF version of the book. So this is supposed to be E, and so is this. Okay. Yeah. Right. So the triple integral of the function f over the domain E, right? This volume integral, can be represented as this iterated integral, right? This triple iterated integral, and you can see that we insert the function f here, r times cosine theta times z, and then I write the Jacobian off to the side just so that I can be clear that I didn't forget it, right? I know some people, they like to immediately write it as r squared, but for me, I prefer being able to reread my answers and understand for sure that I didn't make some weird mistake. So I would put the Jacobian off to the side before I as like my first step, and then I start to clean things up and do my integration. Okay, and you see dr, d theta, dz, and r, the bounds for r are taken from the box. Same with theta, same with z. Okay, so we end up with all of those. And now notice that this function is a product of three functions. Well, it's a product of a function of r, a function of theta, and a function of z. We can split it out into a product of these three types of functions. And so this triple integral can be rewritten as a product of three one-dimensional integrals. Right? That's, we end up collecting the r squared, and you can see that the bounds for r are from 0 to 4. Next I write theta. I didn't have to write it in this order. I just did so because it looked more convenient to do. Theta bounds are there, and then the bounds for z are here. Right? And then, of course, you integrate each of these. That's not so difficult. And then you do the evaluations, you end up with the numbers, and then you simplify, right? So we end up with that as our final answer. Not too bad. Okay. I think the majority of the difficulty for these problems is in understanding what the domain is. It requires a bit of visualization, and I know that can be difficult for some students. So, practice, I guess, is the only thing I can recommend for that. And when you're doing homework, I guess, like, you can use software to check things, but you shouldn't use software on the exam. So yeah, just do enough practice to get accustomed to thinking about these regions. Okay, let's see. This one If I remember correctly, what I did with this, besides changing the radius, is I think I changed sine into cosine, and that does modify things in a slightly significant manner. It's not completely trivial what happens with that. So you do want to be careful about the fact that I'm using cosine, whereas you have sine. Okay, but first let's think through what this region looks like. So this region E that is bounded by a right circular cylinder with this equation, the r theta plane and the sphere. Okay, so right, first of all, hopefully you can see that this is x squared plus y squared plus z squared equals 25. So really this is the circle centered at the origin of radius 5. Uh, I don't know if I want to comment that. Not circle, sphere. Sphere at origin. I won't write it. It's a bit easier if I don't. So first let's think about what this guy looks like. Let's think about what things look like in the r theta plane. So the easiest way to think about this is actually in terms of x and y. So when we plug in, say, theta equals 0, cosine of 0 is 1, so r ends up being 2. So that gives me this point here. And then if you're familiar with how to plot things in polar, you'll know that that this ends up tracing out a circle that is to the right of the origin. So this ends up being a circle of radius, I guess it's of radius 1. The circle of radius 1. Yeah, so the difference is that with sine, your circle is up here. The center of that circle would lie on the y-axis, whereas my circle has center lying on the x-axis. So that's kind of the bottom of the region E. If you try to visualize this, how do I want to do this? I think I actually want to write it like this, x, y, and z now, just to kind of make it match up with this. So you can see that you have this as being the base, and then you have a sphere of radius 5. So 5 up here somewhere, 2 there. You got 5 all the way over here. This ends up being some very large shape, but the point is that this is a cylinder. And then this cylinder ends up you end up cutting out a portion of, from a sphere, you end up kind of drilling out a cylindrical piece of it. The top here is still spherical, the bottom here is flat, and the r theta plane is actually this bottom part here. You have this upper region that is kind of spherically shaped. If I flattened the dimensions, I would end up with this kind of picture. So if you flatten this out, so you have r and z, like so, then like let's say that that's 5 and this is 5. Well, this what's it called? This cylinder only extends to 2, so you end up having a sideways profile of this, which looks like this. So it ends up being this kind of region. Although it's spherical in itself, or it's circular in itself. So there's kind of it's been flattened in a way that is hiding some of the information. Okay. So that's visually what I'm thinking when I am told this this description of this region, that it's bounded by this right circular cylinder, by this r theta plane, and by this sphere. Okay, so now that we have this visual, I can then explain how I got this cylindrical description of E. Well, the theta comes from thinking about how I drew this picture. So notice that this point here was when theta was equal to 0. Right? theta is equal to 0 for that point. So if I sort of trace my way back, I end up getting 0 for the angle theta is equal to minus pi over 2. And then if I kind of work my way forward with theta, cosine is going to equal 0 at pi over 2 as well. So it's to do with thinking about the cosine function, really. So the function cosine starts at 1, and then it kind of, it does this kind of thing. And you should know it goes back, and it does that. But it intersects 0, or it intersects the x-axis at pi over 2 and minus pi over 2. That's why we end up coming back to this, the origin in this picture of this polar equation. So that's how I end up getting my angles for theta. And you'll have to do something similar but different for your your sine of theta. It'll be slightly different here. Okay. Then what do I do next? R. Right. So the thing is that we're trying to define a way to sweep over every point in this solid region E. Okay, and so I should, one thing I should do is I should shade this circle. We want to sweep over this entire thing. So how would we describe that in polar? Well, what happens in polar is that for every given angle theta, you would then have these radial lines emanating from the origin and going to however far they are defined for this shape, which is defined by this equation. So you can see that the maximum value for r is actually going to be given by this equation. That's the furthest extent that we can take. That's why we have that as my upper bound for r. And then my lower bound for r is going to be 0, because that's kind of this other end of the radial line segment. Okay, so that's how I end up with this set of inequalities. And then lastly, how do I get this for z? Well, it comes from here, right? So, let's see, how did I think about this? I mean, so notice that, like, if we were thinking about setting up the integral, you'd have theta as your outermost integral. And then this is now saying that the value or the bounds for r ends up depending on theta. And now z, well, z can either be outside if there's no dependency whatsoever, or inside of things if there are dependencies. And it turns out that there are dependencies, which you can tell from this picture. And you can tell from this function here. So by solving this function for z, right, what we do is we subtract the r squared, and then we take the square root. And if you just take the positive portion, you end up with this inequality. And then the reason that you have that this left portion, this lower bound for z is 0, it's to do with this, actually. It's the xy plane. You can see that when we're visualizing it from this side projection, the bound for z depends on, and maybe I can even write that this function is us drawing r squared plus z squared is equal to 25, but then kind of cutting it off at the right place, because we're told that it's bounded. The region E is also bounded by the r theta plane, which is this line here. This line is the r theta plane. If we didn't have that condition, then you could imagine that this may extend further down, and that it could be bounded by the negative of this square root function. So that might happen with certain types of problems. So you need to read the problem carefully, think about the region, and try to visualize things. But so that's how I end up with these bounds for z, is by considering the side projection. And you can tell that, well, hopefully you're convinced that this is um, the description of the region E in cylindrical. Okay. So now that we have that answers part A of this example. The next thing is to convert the triple integral, which is specified like this. I did this to mirror the homework example. Um, so to convert that into cylindrical. So notice that what I have to do is f is written in terms of x, y, and z, so I have to convert them into r, theta, and z, because that's cylindrical. So I do it like that, because we're not told what the function f actually is. This is the closest way to describe what you would end up actually doing. You would replace x with r cosine theta and y with r sine theta, and whatever that ends up being. Notice we have the Jacobian, right? So because we're in cylindrical, we have the Jacobian r. And we have a slightly different integration order than the standard order. The standard order is dr, d theta, dz. But because of the dependencies of these variables, so notice that r depends on theta, right? And that z depends on r. This actually forces a specific integration order. This forces theta to be outermost, followed by r, followed by z. So you have the order z, then r, then theta. I just reversed those. Right? So you can see that the z integral requires r to be some fixed value. The r integral requires theta to be some fixed value. So that's why this order is necessary. And if you were given a specific function and told to integrate this thing, you would have to do this as an iterated integral. You'd basically have to do it in this order. I don't think there's really any way of changing what this region looks like that would make any sense. I would probably just be forced to choose this, to do it in this order. Okay. Right, enough comments on that. Next problem. So this time we are using b this time. We're integrating over the solid b, the function f, it's triple integral. The function f is this 2 minus the square root of x squared plus y squared plus z squared. You should be able to right away tell that this looks like 2 minus rho. Okay, so immediately that's what I think of. Although there can be some chances where maybe cylindrical would make sense, but this, as well as I guess the region itself, makes me think of spherical. So the region itself, this condition should be shouting out to you that rho squared is less than or equal to 16, which implies that rho is well, rho is rho is between 0 and 4, which is what I wrote here. Then you also have to think about what these two things mean, and I don't remember how I changed these, but I'm fairly sure that I changed both of these, so you have to think about them. These are isolating which octant you're in. So each one of these is splitting your three-dimensional space in half, right? So this one is specifying that the y-coordinate needs to be negative, that's the z-coordinate needs to be negative. So if we think about it, so I'm going to project it in two different ways in order to think about what this region is saying. So y must be negative means that I'm over here. And by viewing it like this, I can determine my angle theta. All right, so this is what I was saying in the beginning about like theta being a bit different from one of the problems. It's this problem. So our region has, well, radius is 4, rho is equal to 4. So we know that it's going to trace out some sort of circle of radius 4, minus 4 to 4. That's not the important thing. The important thing is how do you capture this, how do you sweep over these two quadrants? Well, if you're not wary about the order of the integration, you might have written it as 0 to pi or to negative pi. So, but the problem is, if you think of it as 0 to pi, that would be describing this region, this integration, okay, which is not the correct quadrant, so you'll probably get the wrong answer. If you did from 0 to negative pi, you'd be integrating like this, which almost looks correct, but the problem is that the orientation of this integral is incorrect. Okay, so it's almost like you're, instead of integrating from 0 to 1, you integrate 1 to 0 instead. So that can give rise to problems. That can introduce a negative to your entire problem. So instead, to do this correctly, I want to integrate in this order, in counterclockwise order. Okay, because that's how theta should be oriented, which means that I need to describe this angle here in a way that makes sense, and so that's why it's negative pi to 0. That's why I do that here. Okay. Now for this z portion. So we're trying to do spherical, and so we have this side portrait of things. Z must be negative, means that we're talking about this quadrant. And so thinking about the angle of inclination, right? Thinking about the angle of phi, you can see that over here, this angle for phi would have phi being equal to pi over 2. That's why we get this pi over 2 to pi. That's how we describe this angle, phi. Right, so really phi should be somewhere here rather than there, but it's a little bit hard to draw what I'm trying to draw. Phi is some angle here, and we're drawing this angle, like so. So phi needs to be between pi over 2 and pi, and I believe that converts the entire region B from this Cartesian description into this spherical description. Okay. And then it's straightforward to convert the function f to spherical as well. And so the integral, this triple integral, can then be converted over into this. So you can see that the function f ends up being this, and then this is part of the Jacobian, and I guess I'll underline the entire thing. So that ends up being the dv, right? So that was dv. You have rho squared sine phi coming from the Jacobian, and then of course you do d rho d phi d theta. In this case, we don't need to use any particular order because this ends up being a spherical box. All of these bounds are constants. So you could have used any of the 6 orders. I just wrote it in I guess the standard order, you might call it. So you can see that rho goes from 0 to 4, phi goes from pi over 2 to pi, and theta goes from minus pi to 0. Okay. And then notice that this function that we're integrating over, this can be split into a product of 3 functions, one that just involves rho, one that just involves phi, one that just involves theta. The one involving theta is just the function 1. And so we can write this triple integral as a product of 3 integrals, of 3 one-dimensional integrals, I should say. And so you would then proceed to integrate that. I've mimicked what that would do if you actually integrated this. I didn't bother to do the integration, to write down what the integration is and the evaluation, but hopefully it's clear. Each of these functions should be straightforward to do, and for each of them you'll get these 3 values respectively, and then of course the final answer is you multiply all of them together. Okay. And I believe this should be the last example I have. So, right. So here we have, this is, I would call this the hardest example of the bunch. And I've made this very similar to your problem. So, okay. Converting this region is the hardest part of all of this, and it requires probably more explanation than usual. So this is kind of a daunting expression, I would say. Um, find the volume. So I think that's pretty clear, right? Find the volume means you want to take the triple integral of the function 1 over the region E. So find the volume just means, did I write that below? I did. You want to evaluate this triple integral over E, but you're gonna, in order to do that, you have to figure out, well, does this integral make sense in, I just want to make sure I didn't erase something accidentally. Does this integral make sense as an integral in cylindrical or in spherical? Because it may not be completely obvious which one makes more sense, although I'm kind of spoiling it below. So, because notice that this quantity, this looks like r, right? You remember that r squared is equal to x squared plus y squared. So this really looks like you're saying r. And I'm going to add this extra 0 because it helps me to think about things. It's because the square root function is bounded below by 0, right? It can't be below 0, so that introduces that. We also, if we split this integral, if we split this inequality, we'll get another relationship. So notice if we just think about z less than or equal to this quantity, and then if I square both sides, I get z squared is equal to what's inside the radical. Then I can move everything over. So I end up getting x squared plus y squared plus z squared is less than or equal to 25, which makes me think that rho is less than or equal to 5, right? So you can already start to see like both of these things happen, but this is kind of pointing us in two different directions. One is kind of mentioning cylindrical and one is mentioning spherical, right? This one involving r is more like cylindrical at the moment. So you shouldn't combine different coordinate systems together. That's very bizarre if you do so. So we need to think about what is really happening here. And so the issue is that this is actually a cone. This is a cone with a spherical top. I can kind of visualize it from thinking about this. I guess I have too much experience. Okay, so this inequality, let's think about what this inequality looks like. R and Z. So on the boundary, we would have the equation R is equal to Z. R is equal to Z would be this diagonal line. Do I want to write it as R equals Z or Z equals R? Not sure. But this inequality says that you want the value Z to be higher. So that ends up being, so notice for a fixed value R, they would be equal here at this point, but we want Z to be greater. So it's actually isolating this region, which means that we're really talking about this region. Okay. I actually didn't try to write this in cylindrical to give a good like counter for why you wouldn't do it in cylindrical. There's probably a good reason. I think if you were to try converting this to cylindrical, you would have a relationship between the bounds, whereas in spherical, it's just a spherical box. So I think that spherical for this is easier, but there are ways to describe this in cylindrical if you chose to do it that way. Okay, so what am I trying to explain here? Well, this part I think is pretty clear, right? So this is definitely saying that rho is between 0 and 5. The value for z is bounded above by 25 minus r squared. So it's bounded by this I mean, if I rearranged this, I would end up getting the equation 25 z squared plus r squared is less than or equal to 25. And so that traces out for you a sphere, which would end up being a circle. So you would have a sphere as the upper bound of this three-dimensional region. But then it's bounded below by this, which is the function r, which ends up being a line in this projection. So you can see that that this spherical cone, if we revolve it around the z-axis, that is what the solid E looks like. Okay, it is a cone with a spherical top, and so that is what kind of tells me that it makes more sense to do this in spherical. And let's see, r or rho rather goes from 0 to 5. Then, in order to convert this to spherical, you have to then describe the angle of declination. Which the way that I would tell this from the picture is thinking about what this angle is. Right, this angle that you make, that this line r equals z, what angle does that make? So because it is a line of slope 1, this is a 45-degree angle. Right, this angle here, it's a 45-degree angle, which means that this angle is pi over 4. So the angle of declination, or the angle phi, starts at phi equals 0 and declines down to pi over 4. That's why I write that. And then these last two guys, what they are doing is they're fixing where we are in polar. They're fixing our angle theta. So if you draw the xy plane, if we project ourselves so that we're looking at this region positive z-axis down, well, this would end up looking like a circle of radius 5. And then these two are cutting the quadrants, so we end up having x be negative and y be negative, which specifies the third quadrant. And then this third quadrant is precisely why I have my angle theta here. So this ends up being theta. So theta goes from pi to 3 pi over 2 is given by these two. Okay. My scratch work is a little bit messy, but hopefully you'll follow that. You'll follow it from the video at least. Okay, so we have that, and this is a spherical box, which makes setting up the integral pretty straightforward. So you see that 1 becomes 1 here, but I suppressed writing 1. You have this, which is coming from the differential for element for volume. So all of this is your dv. Right? So that is equal to dv. The rho squared sine phi is the Jacobian, and then I'm keeping the standard order for spherical d rho, d phi, d theta, which is fine since this is a spherical box. Any of the 6 integration orders could have worked. So you can see that I'm writing rho going from 0 to 5, phi from 0 to pi over 4, theta from pi to 3 pi over 2. And this is a product of 3 functions. This can be separated out into a product of a function involving rho, involving theta, involving phi, all separately. And so I do that, and then I mimic integrating it. So I didn't write I skipped a step in between where you do the integral, but you have the evaluation bar, because I think that it should be straightforward for you to see how that works. And then lastly, I end up simplifying the computation. So you would end up with this quantity, whatever that quantity is, and that will be the volume of the region E. Okay, and just let me quickly mention this. So I'm just doing this because I know that some students will, I figure some students might do this, where they just copy down the answer, but then they don't actually do anything. So I don't know how the graders grade, but if I was grading it, if I just see an answer without any work for these problems, I would not give any points, because it is pretty obvious that these problems cannot be done without showing some amount of work, right? The point is that there's difficulties in setting up the integral and then in evaluating the integral. If I show you what the integral is that you should compute, that spoils too much. So I'm showing you as much as I feel comfortable with showing you, so that you can at least verify that you got the right answer at the end. So if you don't get these answers, that the error can be in one of two places, right? Doing the integration or in setting up the integral. You can always check your integral computations with Wolfram Alpha, although it may not show it to you in the format that you think is the same. So, like, I think like with this one, it might do something funny with the numbers. I'm not sure exactly which one, but sometimes it'll give you an equivalent answer that just looks different. So you just have to fiddle with it a little bit to double check whether you got the right answer or not, or maybe you use a numerical approximation to check if your answer is equal or not. But yeah, definitely. Um, um, Set up the integral. Try to do it correctly. This topic can be a bit tough when you are first introduced to it. So, yeah. All right. I guess that's it.